Right, so the next thing we're going to talk about here is ions. So I've reproduced the cartoons for a couple that you've already seen, namely the hydrogen ion here, the carbon ion here, and I've added two more, a representation of an oxygen ion and of a sodium ion. Now I need to clarify one thing before we go on, because it didn't print out very well. What's in this box right here should actually read 23 Na plus. The plus sign is kind of hard to see the way that printed out. So here's a question. What distinguishes a neutral atom from an ion? So look at those, and if you have to, go back at your notes and review those to compare what the carbon and the hydrogen look like without it. And then look at these. And so hopefully what you found is that the number of protons and electrons in those atoms are different. And if they are different, then it becomes an ion. If they are the same, they are a neutral atom. So the next thing you need to be able to do is figure out, given a picture or like this, or the information contained in that picture, is how do you determine the charge of an ion. And this is a case where I think math is actually a much more efficient language than English or French or Spanish is. And it's just the difference between the number of protons and electrons is how you get overall charge. And if you do it this way, defining the charge as the number of protons minus the number of electrons, you will get the sign of the charge right. And while we are here, I want to give you two more new words. And ions that have a positive charge are referred to as cations. And ions that have a negative charge are referred to as anions. And probably the sooner that you make that association, the better, because those are words that chemists use all the time. All right, just one more slide with cartoon boxes like this. And here it is, and this is going to be all about the masses. So I've reproduced the 3 hydrogen isotopes for you and the 3 carbon isotopes for you. And now your question is this. How is the mass number, often referred to as A? Now that, in this case, is the left superscript. So, you know, the 1 or the 13 here. Based on the information in there, tell me how you think we got those numbers. Right. Based on what you've seen there, it seems to be roughly, not roughly, but equal to the sum of the number of protons and neutrons. Now this is, and you'll look, there's a pretty strong correlation between that integer number, 1, 2, 1, 13, and the actual mass in atomic mass units. That's what the AMU stands for, by the way. So hydrogen 1 has a mass of about 1.0078. Hydrogen 2, also called deuterium, has a mass of 2.104. And you can see that in all of these cases, if you were to round these numbers to the nearest integer, it would be equal to that mass number, and then just equal to the number of protons and neutrons. So this will also probably lead you to believe that, actually I want to hold off on that. I'll just give you the next question. Where does most of the mass of the nucleus reside? Is it either inside the nucleus or outside of it? And remember, the nucleus is this tight little ball of protons and neutrons here, and the electrons are not part of that. So, you know, if you want to, take a look, hit pause, think about it for a second, come on back. Now, to figure this out, what you want to do is look for 2 species whose mass differ only in, or whose makeup differs only by the number of electrons. And we have two such examples. So one here is carbon-13 and carbon-13 minus. So they only differ in the number of electrons. So this one has 6, this one has 7. And look at the precise mass. 13.0034, 13.039. So that implies that extra electron adds 0.0005 AMU of mass. Meanwhile, each proton and neutron seems to add about 1 AMU. And you get a similar result, actually exactly the same result from here. Hydrogen and hydrogen 1 minus, also called hydride, differ by 1 electron. That extra electron seems to add 0.0005 AMU as well. So most of the mass really does seem to be within the nucleus, and that's simply because the electrons, which are the only ones that are outside of the nucleus, are ridiculously light compared to the protons and neutrons. So, and it's like, rounding error. So to recap, the mass of the neutrons and the mass of the protons are almost exactly the same. And rounding to an integer value, they are 1 atomic mass unit each. The mass of the electron, however, is about it's a little more than 1/2000th or 1/1820th of the mass of a proton. So while electrons do have mass, it's just a lot smaller. And if you are, again, you can see here that you have to take the mass out to the 4th decimal place to see that difference. So practically speaking, almost all of the mass is in the nucleus and not outside. All right, so let's do one more learning check for this material, which is grouped together is referred to as the nuclear atom. So I could ask you a question like this. A oxygen 18, which is how you would verbalize this right here, contains the same number of protons, neutrons, and electrons. True or false? And explain why. So hit pause, think about it, come back. All right. Hopefully you came up with false. So let's take this apart here. This is a neutral atom, so you know that the electron count and the proton count must be the same. And it's oxygen, so that tells you that it is 8 each. But the mass number right here indicates that, so you've got a mass of 18, 8 AMU comes from the protons, meaning you've got 10 neutrons, and in most counting systems, 10 is not equal to 8. And the other indication of mastery that we look for is if you can, basically fill in tables like this. Given a isotope symbol, like these guys, tell me how many protons, neutrons, and electrons are in each of these isotopes. And feel free to use a periodic table to work with this. You will need one. And here are the answers. All right, so I'll just pick one as an example here. So let's look at sodium. And that is a typo that I will fix right now. That is actually sodium plus. All right, and hopefully those numbers now make sense. So sodium is element 10. I'm sorry, sodium is element 11, which means it's got 11 protons in it. The total mass is 23, so 23 minus 11 is 22, so that implies there are 22 neutrons. It's a +1 ion, so that tells you that it has 1 electron fewer than it does protons, which gives you a total of 10 electrons. And be sure you can do the same thing for all of these, and you should be fine for any exam question you're going to see on this material.